In this video, we're going to talk about the three phases of matter, and we're going to describe their characteristics at the atomic level. Just to review, we have our three phases here. There's our solid, our liquid, our gas, and these are our phase changes between them. So we should know at this point fusion, solidification, vaporization, condensation, deposition, and sublimation. And so those should be old, so I'm not going to review them. So now let's look at the three phases themselves. So if you look at a solid, the molecules are really close together. So the way I like to do this is I'm going to start with the very first thing I notice, and then I'm going to explain how these characteristics affect everything else. All right. So in a solid, the molecules are really close together. Therefore, if you look, they're so close that they're basically touching. So if you think about this in 3D, not in two dimensions, yes, in 2D it looks like this, but in 3D there's also rows going in and out of the paper. So if the molecules are literally stacked together like that, do you expect them to be able to move? And the answer would obviously be no. They can't move. They can vibrate. In other words, they can sit there and buzz, and molecules do that, but they can't change positions because there's physically not enough room for them to move around because they're packed in so tight. So they can't move. They only vibrate without changing their relative position. That just means they can't trade places. Because of that, do you think if you try to squeeze them together, you'd be able to make them get any smaller? Well, obviously the answer is no, because there's not really any space left to make them get any closer together. So we say that they're not easily compressed. And another way of saying that is that they have a definite volume. So their volume won't change if you squeeze them. That doesn't mean you can't change the shape. It just means you can't make it take up any less space. We also see, because they can't move and they're all in this geometric row, we have what's called a repeating geometric pattern. That is a characteristic of a solid. Sometimes they use the word geocentric instead of geometric, but it's basically the same thing. And because they're in the solid phase, they have, under normal conditions, they have a definite shape. Now, I mentioned earlier that you can make them change the shape. The only way that would really happen is if you melted them and then let them refreeze, essentially. So under normal conditions, they have a definite shape. For example, a rock. A rock is a solid, and it has the molecules themselves are not moving. They can vibrate, but they're not changing their position. If you squeeze the rock or try to compress it, you're not going to make it any smaller, as opposed to like a marshmallow, right? Because it's marshmallows, even though we call them solids, they're actually mainly filled with air. And there's a repeating pattern, but we can't see it with our naked eye, and they have a definite shape. If I take a rock and put it on a table and come back in a month, a year, or a decade, it doesn't make a difference. It's going to be the same shape. It's not going to change. Obviously, if something heated it up to melt it and then it reformed, that's a different story. We're really excluding that. Now, if we look at liquids, what's the difference between a liquid and a solid? Well, if I look at the two diagrams, the only real difference is, one, I don't see the repeating geometric pattern. They're kind of randomized. That's one difference. And two, if you notice, there's a tiny little bit of space between the molecules, much more than than a solid. And that little bit of space allows molecules to essentially slide past each other. So the molecules are far enough to slide past each other. That means they're free to move. That's why you can pour a liquid, but you can't pour a true solid. They are still not easily compressed because if you look, there is a little bit of space, but it's not much. So while you can compress a liquid a tiny, tiny, tiny bit, it's so small that we ignore it and we just say that they're not easily compressed. We just lump them in with solids. In truth, they can be compressed a little, but we're talking about less than 1%, so it's not really worth mentioning. So they have a definite volume as well. They do lose their geometric pattern because they're randomized and because they can move, and therefore because they can move, they have no definite shape. They fill the container. What that means is that if I pour a gallon of liquid into a gallon container, it'll fill the liquid. If I pour it into a 1 gallon container that has a different shape, it'll fill that container. Liquids always do that. Now, one thing I want to mention is I said that liquids are free to move and that solids cannot, and that is true. Do not confuse a true solid. Like, for example, you can pour a liquid. Well, a lot of people would say, well, yeah, I can pour a jar of sand too, but these sand molecules are individually freed up, whereas in a liquid, to be a true solid, all the sand molecules would have to be interconnected like a rock, whereas if you have tiny little pieces like sand or marbles or anything like that, that's actually, it's not a liquid, but it's kind of behaving like a liquid, so we don't count those. So when we think of pure solids, think of like a brick or a rock, not sand. That's a poor example because they're not connected. So that is for the liquids. Now let's go to the gases. The gases, if you notice, the big difference is they're really far apart, and this diagram is actually not very accurate. They'd be way further apart than this if the diagram was accurate, but we wouldn't be able to really make a good diagram because there'd only be like one single atom in this entire diagram. That's how far apart they'd be. So we draw them closer together than they actually are, only because it's inconvenient to draw them as far apart as they are in real life. All right, so that's one thing about the gases. And if you notice, they have these little streaks on them. That's basically to show them like moving really fast. Think of it like if you ever see a something like a ball that's a baseball that's getting hit. It almost kind of looks like a blur if it's moving so fast. That's kind of the idea. We're just showing that they're moving around in random different directions at really high speeds, or that's what we're trying to show. So the molecules are very far apart. They move at high speeds. They're constantly colliding. They are compressible. In other words, if I take a gas and I try to squeeze it, I am going to make it get smaller because all this empty space between the atoms, there is room for the atoms to get closer together. So we say that they are easily compressed, therefore they have no definite volume. Their volume can change without changing the amount of gas atoms. I can just make them get closer together, or I can make them get further apart just by squeezing or pulling. There's clearly no geometric pattern, and they definitely have no definite shape. They always fill the container. You're in a container. The classroom or at the room that you're in right now, or even if you're outside, the earth, there's a container around and it's filled with air. It's not like if you move to a different part of the room that there's going to be less air in one part versus the other. It fills the container evenly all the time. So that is the notes on this. It's a pretty easy topic. And now the next thing I want to do is I want to go over a couple multiple choice questions. These will be similar to what you'll see on Castle Learning. I just want to go over a few of them. So let's look at number one. Number one says, the characteristic which distinguishes a true solid, notice they threw the word true in, that's getting rid of the whole like sand example, from other phases of matter at STP. STP just means standard temperature and pressure. At this point, we're just going to ignore it. Well, I'll explain what it means later. Is that a true solid, the particles are what? So are they vibrating without changing their relative position, or are they motionless, truly motionless? Well, they're not motionless. So right off the bat, as soon as I read that, I'm getting rid of B and C. So now the question is it A or D? And so are they vibrating without changing their relative position, or vibrating and changing their relative position? Obviously, the answer is circled. Number two, which particle best represents, or diagram best represents, a monoatomic gas? So you've probably already guessed, but let's get rid of the two. They want a gas, right? So clearly not A. A would technically be a liquid because you see there's no repeating geometric pattern. And then D would be the solid because there's the repeating pattern. So it's not A or D because they want a gas. It's either B or C. Now notice the word monoatomic. That means one atom. So monoatomic would be C. Diatomic, we would call it diatomic if there's two, would be B. Question three, it's diatomic gas, so it's the other question. Obviously the answer is D. And down here for 4 and 5, they're pretty simple. Which set of properties does a substance such as CO2 with a G in parentheses have? So I want to just go over this. The G in parentheses, if you haven't figured it out, means gas. So the CO2 part is irrelevant. What they're really asking is which one of these four things defines a gas. So definite shape, clearly not. We know gases, they change their shape all the time. Same with liquids. So A and C are totally wrong. So it's got to be B or D, no definite shape. And then the question is, do they have definite volume or no definite volume? And if you go through the notes, you'll obviously know that they have no definite volume. And then the last one I'm just going to mention is, which sample are the particles arranged in a regular geometric pattern? So if we look at these questions, we see lots of options. Do not worry about the chemical formula. That actually is irrelevant. What they're talking about when they say regular geometric pattern is a solid. So what I'm really looking for is the one with the S in parentheses. Just to review, S in parentheses is for solid. L in parentheses, they usually use a script L. I don't know why, but the L in parentheses is liquid. The G in parentheses is gas. And the AQ in parentheses, which you probably haven't heard before, means aqueous, which if you haven't guessed already based from that word, it is dissolved in water. So NaCl AQ literally just means NaCl is table salt, and the AQ means dissolved in water. So this is just a fancy way of saying salt water. All right, so that includes these questions. Number 6 is basically the same question, just different options. There will be a Castle Learning on this. Hopefully that will make the Castle Learning a little bit easier.